I think the minute is more or less over. So let's start. Welcome, Peter Stopp from Gamma Technology. Gamma Technology is one of our JMAG and PowerSys partner. And Peter Stopp will give a presentation about multidisciplinary approach to integrated motor modeling using GT Suite and JMAG. He will give a presentation about 30 minutes, perhaps a little bit longer, a little bit more, we will see. And after this, he is available to answer your questions. Please ask your question via Zoom in the Q&A section or in the chat. And yes, my name is Martin Michels. I'm responsible for the PowerSys office in Frankfurt, Germany. And I'm hosting this presentation. So regarding our speaker, Peter Stopp from Gamma Technology, he has studied automotive engineering at the University of Stuttgart. He joined Gamma Technology end of 2010. He used to work in the thermal management team, meanwhile focusing on vehicle and electrification topics. Peter Stopp, welcome and wishing you a good presentation.
Thanks a lot for the kind introduction and welcome and still good morning to everyone. Start to share my screen once I have the rights to do so.
You don't have? I will.
Not yet.
Okay.
Oh.
Let's see. Can you share it now?
Yes, now it works.
Okay, perfect.
Perfect. Okay. Believe you can see my screen?
Yes.
Very good. Then, yeah, perfect. Then again, hello everyone, as said, and thanks again for the kind introduction. And also thanks for the opportunity here to present at this conference. It is my pleasure to be speaking to you today about the title that was already named. So a multidisciplinary approach to integrated motor modeling using GT Suite and JMAG. See, perfect. So for the presentation today, I will cover several topics. First, starting with an introduction to Gamma Technologies, then some product highlights of the GT Suite. Next, I will examine the need for integrated multiphysics simulation. And I will introduce the partnership that GT and JSOL have created, which brings us then to the real purpose of the presentation, namely, which is demonstrating to you our solutions for integrated noise, vibration, and harshness solutions, so NVH. And obviously, as always, concluding with a summary. Okay, so Gamma Technologies, not every one of you might know the company. So we are a software development company with the headquarter being based outside of Chicago in the US. And we were founded in 1994 with the goal of providing system-level multi-physics engineering software. Since the founding in 1994, we have expanded the offices also to Europe. So Stuttgart, that's where I'm located basically. But we also expanded it to India and are also represented in the Asia Pacific region by IDHA. We have a singular focus. It's really the development and the support of the GT Suite software around the globe. The product, our only product, the GT Suite, is a multi-physics modeling platform designed for CAE engineers to quickly build models at the appropriate level of fidelity to solve the task at hand. GT Suite contains electrical libraries to build any kind of electrical circuit, including elements such as map-based inverter motor subsystem for complete vehicle energy assessment, but also switched inverter motor assemblies if you look into motor drives and NVH. The software also models thermal systems, such as thermal networks of motors, battery assemblies, and these models can be represented in different levels of fidelity, starting from what we can see now on the screen, the lumped mass models, up to even complete finite element structures, and also couple with the electrical and the fluid flow solution. Speaking of the fluid flow, the flow library is also built upon a 1D CFD approach. So we're solving Navier-Stokes equations in one dimension. So predictive modeling of effects such as priming and also two-phase flow is doable and easy handleable with the software and the solver. For model building, we offer a seamless integration with CAD modeling for easy conversion of CAD, so CAD models into CAE models. These models can now be coupled together with mechanical models. So for driveline, for example, seeing here driveline mechanics, also vehicle dynamics can be captured, and all the way to also higher frequencies important to capture for NVH investigation. Since GT contains really a mix of deep physics together with system level capabilities, we have worked to provide users the capability to develop the next generation powertrain and also the vehicle architectures. Working with many customers in different market segments and geographical locations, we have seen one common theme, basically, which is the increasing need for closer collaboration between the different departments. And as electrification now brings new powertrain challenges, together with pressures to decrease the development times, increase the overall powertrain efficiency, and also decrease cost, the need for this kind of collaboration between the different departments is higher than ever. However, we have also seen that traditional workflows and processes are decoupled. So the motor experts typically work largely in isolation from other teams, such as the control, the thermal, and also the NVH engineers. They typically need to integrate the motor in their complete powertrain system. And this decoupledness doesn't help here, certainly. So these teams are typically only exchanging component requirements and inputs and outputs. While this way of working has historically yielded appropriate results, it is inefficient and suboptimal as information, assumptions, and models are not shared across department boundaries. And this really leads to redundant, sometimes even incorrect work. Now, in coordination with JSOL, we have developed a more streamlined approach suitable for every stage of the development process, starting with the system level analysis for electrified vehicle architectures. At this stage, the motor representation is typically efficiency maps, which characterize the motor behavior as a data-driven model. And this type of model is useful for determining component sizing and overall powertrain efficiency. For this stage, we have integrated JMAG Express Online into the GT suite. As the program develops, the models with more predictiveness and fidelity are developed and are needed. And in motors, starting by defining the motor architecture, which meets the vehicle level requirements. And for this stage, we have direct import of motor behavior specifications from JMAG. Eventually, detailed 2D and 3D electromagnetic analysis must be accomplished. And for this level of fidelity, GT relies on established partnerships with the tool of choice used in the industry, JMAG Designer. These electromagnetic models can be reduced to represent the mechanical and thermal behavior of the motor, basically, for the purpose of control, thermal, and mechanical integration. Eventually, these final design models are reintegrated into the complete vehicle system for MIL, SIL, and HIL calibration via JMAG RT. And for my presentation today, I will concentrate on the motor integration topics, now specifically for NVH. When we look at NVH phenomena, these can be broken into different areas depending upon the frequency range. So typically vibration problems are lower frequency and can be solved by using 1D multi-body dynamics approaches. And some of these phenomena include vehicle shuffle, judder, and clunk. Other phenomena require either a fully 3D or a coupled 1D 3D approach, such as rattle, imbalance, and boom. And as frequencies reach higher levels, higher fidelity models are required, typically in the form of finite element flexible bodies. These can be included, or these can basically include models such as clunk and whine, which manifest themselves not as vibrations felt by the occupants of the vehicle, but more like an audible sensation. When we now look holistically at next generation vehicle and powertrain architectures, and now in particular on battery electric vehicles, we can identify that those noise footprint of those vehicles is different compared to an internal combustion engine powered vehicle. So this is specifically true at low vehicle speeds where wind and road noise are typically low, and the electrical, the auxiliary, and also the powertrain noise dominates. Looking in more detail at this problem, we can see that in the case of the combustion engine, many NVH factors were masked by the engine noise. So with this noise now gone, the occupants of the vehicle will experience new sound and vibration sensations. As previously mentioned, these sensations may emanate from the e-motor or the e-axle system, as well as accessories and HVAC systems, which are increasingly important, of course, for cabin comfort, as well as powertrain and battery thermal security. In the presentation here, I will focus mostly on e-motor and gearbox dynamics. And as we can see on the upper right corner of the slide, the noise profile of BEVs in blue is typically lower than combustion engine powered vehicles. However, at certain important frequencies, depending on motor design and packaging, the noise footprint of BEVs can be disruptive to the vehicle occupants. We've seen that because of this new noise profile, regulatory bodies are taking notice and issuing new regulations on vehicle noise profiles, especially at lower vehicle speeds for the purpose of pedestrian safety. And obviously, this now makes acoustic CAE much more important. The process now to determine these new noise sources is very complex, and it requires a full suite of multi-physics interaction. Starting with the power control unit, the inverter will provide electrical excitation to the motor, and this excitation itself may create a noise in the wiring. Now, depending on the motor construction and the quality of the electrical waveforms, the motor will respond and magnetic forces will be developed in the stator. These forces and ensuing stator vibration will be transmitted to the powertrain through a mechanical transfer path. The forces from the previous step are then used as boundary conditions for powertrain analysis. And for this, a full multi-body dynamic characterization of the powertrain machinery components must be performed, including submodels for bearing and also gear geometries and loads, shaft dynamics, and different machinery loss models. Third, a full FEA analysis on the housing structure is performed, reacting from the loads from the magnetostatic analysis and the vibration from the powertrain transmitted through the bearings. And then fourth, in order to understand the radiated noise, there is an aeroacoustic analysis required to resolve the radiated noise field of the powertrain. Whereas the previously mentioned solutions are part of the GT suite for now quite some time, the aeroacoustics analysis is a relatively new addition to the software. To enable now this process, we take advantage of the electromagnetic force output for NVH from JMAG Designer. This allows GT to import the local forces on the stator for mechanical excitation. The electromagnetic forces files get exported in CSV file format, which GT reads in directly. And these files give the X and the Y direction forces as a function of the rotor angle at each local stator tooth. These forces are then applied as boundary conditions to the stator mesh, which has been merged with the mesh of the gearbox housing in the case of an E-axle here. The excitation forces from the electromagnetic model act as boundary conditions within a larger model, including the gearbox housing, as well as the gear train, the shafts, and bearings. This allows a one-way coupled simulation such that the forces will affect misalignment of the gears and therefore housing deflections, which are all solved in the time domain. These housing deflections create surface vibrations, which excite the surrounding air and also create noise. So a future step will look at eccentricity in the electromagnetic solution for a full coupled analysis, such that this misalignment in the rotor due to bearing and gear deflection will also influence the electromagnetic excitation forces. As we have now discussed that noise comes from surface vibrations of the e-axle, for example, we need to look in detail at what else, besides electromagnetic excitation, will contribute to these surface vibrations of the housing. Looking at the gears, there are many elements that can cause high frequency harmonics to the gear train, which is used to multiply and distribute the motor torque to the vehicle wheels. And the dynamic phenomenon, such as tooth tip contact, the local deformation and the misalignment, now either due to installation errors or to the dynamics, as well as also gear shuttling forces and friction can be contributors to higher order harmonics. But in addition to that, there are also manufacturing details such as machining imperfections that can contribute to higher order dynamics. It is important to capture these phenomenon when looking at this coupled problem. Of course, gears do not operate in isolation, but typically rather connect to the housing structure through the bearings, which requires also a model. And within GT Suite, we provide bearing models based on ISO standards for various bearing types. These bearings transmit the dynamic loads within the gearbox to the flexible housing structure using condensed nodes. To begin to study the vibration for the e-axle housing, we start by extracting the loads on the e-axle housing from the previous coupled multi-body dynamics and finite element time domain analysis, and by taking a fast Fourier transformation of these forces and applying them at the boundary locations, for instance, the bearing locations or stator tooth, we can now make a linearized forced frequency analysis of the gearbox structure. This allows us to resolve the operating deflection shapes at a particular frequency and allow the user to investigate frequency response at the nodal locations of interest in the form of Campbell diagrams. Once the operating deflection shapes have been resolved across the frequency range of interest, it is possible to perform the acoustic analysis. And there are various methods to perform this type of analysis. One of these methods is the monopole solution. By placing a monopole at every node on the mesh, which you can see here on the figure on the right, we can track surface vibrations on the body, which generate sound pressure levels for each monopole at the microphone location. These are then summed together at the microphone location so that the noise profile can be captured. For runtime purposes, we omit monopoles which are occluded from the microphone by the body itself. Comparing this technique against more computationally expensive techniques has so far yielded promising results, as we can see on the plot at the bottom. Another possibility to solve the acoustic signature of the vibrating axle housing is the wave-based technique. Here, I'm showing our new solution for acoustic performance using the wave-based technique. And the advantage of this technique is that it is accurate and it allows for faster results than some conventional FEM and boundary element techniques. On the right side, you can see some operating deflection shapes of the housing at different frequencies, as well as the sound pressure levels associated with those frequencies. So far, I have now shown the GT and JMAG coupled solutions, which allow engineers to model an e-axle assembly, starting with the motor and tracking performance all the way to the system acoustic signature. Clearly, this analysis is very powerful and detailed. However, it does not represent the only solutions that GT and JSOL have tackled for NVH challenges. As many of you are likely familiar, there is another avenue besides the electromagnetic NVH force export to be used in system models, and this is via JMAG RT. With JMAG RT, it is possible to export the RTT file, which contains rotor angle dependent flux linkage maps. And this allows the GT system level tool to utilize JMAG RT to predict e-motor transient torque, including cogging torque, and we can apply various motor drive technologies such as MTPA, field weakening, and SVP-VM to track the motor response at the complete driveline and vehicle level. In such an integrated model, we can evaluate torsional NVH responses due to engine, motor, and damper interactions. And this allows for earlier, more upfront NVH analysis, which previously has not been possible. Together, GT and JSOL are working to reduce obstacles to collaboration. And by creating streamlined workflows that allow motor design experts to work closely with the integration teams, we have enabled more seamless model and result sharing, which brings efficiency and transparency to the design process. This already brings me to the end of the presentation. Thanks a lot for the attention. And again, thanks a lot for the opportunity to present our joint work here at the conference.
Peter Stopp, thank you very much for this presentation. And now I think you are still available to ask, respond to answer questions. Please write your question in Zoom in the answer and question section if possible. Normally we still have to wait a little bit for the first question.
Okay, maybe I can start the conversation.
Yes, of course.
Okay, so thank you very much for this interesting presentation. First thing I wanted to ask was, for the NVH, what else can GT actually consider something else except other than NVH behavior coupled with JMAG or coupled with motor when? So as you said in your presentation, we need to have sort of a full field of everything and have all the departments sort of linking together in the end, and not just having the electromagnetic in one side and then just mechanical in the other side. The whole point of working with GT and is actually linking all of these together in the end. What else can GT consider?
Yeah, no, absolutely. I mean, I had this overview slide. Covers the different domains we typically work with, right? It's certainly thermal that we have to talk about here, fluid flow as well, and entire full system behavior. So certainly thermal, if I start with thermal aspects, there we also work on developments in having a streamlined process in writing out local losses directly. We in GT have a finite element thermal solution where we can easily impose losses calculated by JMAG Designer. So this is one idea we have. Typically, as said, since we are solving the full system, including powertrain, vehicle, batteries, thermal system, HVAC, cooling, a direct coupling with a 2D or 3D electromagnetic tool is not the preferred way because it takes too long, right? But really having a streamlined process, not only in one department sends loss maps to a neighboring department, we really want to have a more integrated approach, exporting files from JMAG Designer directly imported into GT, having a streamlined process at different stages of the development cycle, right? So having an automated process is easier to track and then to improve if there are different evolution stands of the e-motor existing, better than just copying maps, right? Direct linking kind of makes sense there at this point. Yeah. Hopefully this answers the question.
Yeah, this answers the question.
Okay, good.
Very much.
Okay. Other question from your side, Ahmed? Or...
No, I think the presentation was very clear.
Okay, yes. Okay, then Peter Stubb, thank you again for this presentation, for having answered the questions.